So there's two things we can do in space. And you can look for the volume of solids, or you can look for the area of surfaces. So let me start with the easier of the two. Let me start with volumes of solids. And we'll go back to area, I promise. So I claim that there's also a notion of determinant in space, and that's going to tell us how to find volumes. So let's say that we have three vectors, A, B, and C. And then the definition of their determinant is going to be, so the notation for that in terms of the components is the same as over there. We put the components of A, the components of B, and the components of C inside vertical bars. Okay? And of course, I have to give a meaning to this. So this will be a number. And what is that number? Well, the definition I will take is that this is A1 times the determinant of what I get by looking in this lower right corner. So the 2 by 2 determinant, B2, B3, C2, C3. Then I will subtract A2 times the determinant of B1, B3, C1, C3. And then I will add A3 times the determinant B1, B2, C1, C2. And each of these guys means, again, you take B2 times C3 minus C2 times B3. And this times that minus this times that, and so on. So in fact, there's a total of 6 terms in here. Okay, and maybe some of you have already seen a different formula for 3 by 3 determinants where you directly have the 6 terms. It's the same. Okay, it's the same definition. So how to remember the structure of this formula? Well, this is called an expansion according to the first row. So we're going to take the entries in the first row, A1, A2, A3, and for each of them, we get a term. Namely, we multiply it by a 2 by 2 determinant that we get by deleting the first row and the column where we are. Okay, so here, the coefficient next to A1 is, well, we delete this column and this row, and we're left with B2, B3, C2, C3. Next, the next one, we take A2, we delete the row that's in it and the column that it's in, and we're left with B1, B3, C1, C3. And similarly with A3, we take what remains, that's B1, B2, C1, C2. Finally, last but not least, there's a minus sign here for the second guy. Okay? So, well, it looks like a weird formula. And I mean, it is a little bit weird, but it's a formula that you should learn because it's really, really useful for a lot of things. So I should say, if this looks very artificial to you and you'd like to know more, there's more in the notes. So read the notes. They will tell you a bit more about what this means, where it comes from, and so on. If you want to know a lot more, then someday you should take 1806, linear algebra, where you will learn a lot more about determinants in n-dimensional space with n vectors. And there's a generalization of this in arbitrary dimensions. In this class, we'll only deal with 2 or 3 dimensions. Yes? Sorry, why is the negative there? Well, that's a very good question. It has to be there so that this will actually equal, well, what I'm going to say right now is that this will give us the volume of the box with sides A, B, C. And the formula just doesn't work if you don't put the negative. There's a more fundamental reason which has to do with orientation of space and the fact that if you switch 2 coordinates in space, then basically you change what's called the handedness of the coordinates. If you look at your right hand and your left hand, they are not actually the same. They are mirror images. And if you swap 2 coordinate axes, that's what you get. That's the fundamental reason for the minus. But again, I mean, we don't need to think too much about that. All we need in this class is the formula.